Okay, well, so welcome back, and I'm going to talk to you about photonics. A little bit about my background. Most of my career was actually in the private sector at Bell Laboratories, which was really a mecca for optical communications and photonics. And as with many people, I went there thinking I was going to do the Bell Labs thing and work for a year or two and then go be a faculty member. And a lot of my colleagues did that, but I just had too much fun. And I couldn't tear myself away for many, many years. Ended up there as a vice president and also chief technology officer for their opto business and vice president. And then finally went into the world of academics. So I've been in academics for about, well, let's see. It's about 11, 12, no, 13, 14 years now, I guess. So I'm not new to the world of academics, but I still remain as excited about photonics as I was. So I was thinking over the weekend, this is a talk I haven't given before. I was trying to come up with something a little bit different, and I was thinking about what I did over my holidays. And we went up to San Francisco, and of course it's very beautiful up there. The reason I'm showing it is we went just for fun. We wanted to go somewhere different. We went to this place called Point Bonita Lighthouse, which you can see where it is. Here's the Golden Gate Bridge, and it's out there on this point. And the reason I'm showing it is because it's photonics everywhere. So I was out there just with friends and family on a sunny day, and you go up and you look at this lighthouse, and it's got this incredible Fresnel lens in it. And if you look in there, there's these suspended rings. You can see the air gaps there. It's really an amazing piece of optics. But again, the reason I'm showing it is because it's not just optics. Now it's photonics. And why am I saying that? Well, just this year, earlier this year, they changed out the light source. So here's a picture of the diagram of these Fresnel. This is some old text out of something from Fresnel back in the early 1800s. This thing was put together around 1850, and they used what's called a second order Fresnel lens. This is just the size of this thing, and you can see the main element here, but then all these other elements capture about 70% of the light. And it was made to work with an oil or a kerosene lamp back in the day, around 1870, when it was lit up in its current location. But now, what do you do in 2016? You upgrade. So they upgraded this thing to an LED light source. And I just found it incredible. If you look at the example of the kinds of LEDs they're putting into something like this, these are kilowatt equivalent optical power sources, and they allow you to see out to 15 or so nautical miles at night. And if you look at each one of these little elements, this is new stuff. Just 2 years ago, the Nobel Prize was given to Shuji Nakamura and some colleagues for coming up with this indium gallium nitride LED system, which puts out UV photons. So it's the whole idea that you could make an LED with a photon so big that it could hit a phosphor, and that's how they get the white light out of these things. They hit a phosphor and it fluoresces, but the wavelength is so short, the photon energy is so big that it can emit essentially the whole visible spectrum and look like white lights. And of course, now you go to Home Depot, you go everywhere else, and all your light bulbs are getting replaced by LEDs. But when they're even in the lighthouse built in the 1800s. They kept everything else the same, but they changed out the bulb. To me, that's kind of an interesting statement. So, optics is everywhere, and I showed you this morning. We all live in the world of optics and photonics, with people assuming we work with eyeglasses and things like that. But I hope to show you, at least in this, that there's a whole. We'll do this in layers through the next couple of days, but there's just whole other fields that are dramatically different. And one of the best examples of something that's near and dear to your heart is a cell phone. You might think of the things you can think of here that are optics in this. Maybe the most obvious one is the display that's on there. You see everybody with their little props on the airplane seat next to you watching movies on these things. So it's a pretty darn good display on there. Very high quality, and the technology that goes into making that display is both incredible and very advanced optoelectronics. But there's more, a lot more to it. Even the machine casing, so this is made out of molds that are machined with laser beams to get the precision they need in there. That's part of it. We all know about the cameras, so there's a camera in the front and back. This is a diagram. I wish the light was down a little bit. I don't quite know how to do that. Maybe Miss Sid does. We could improve the quality of the image a little bit better. Oh, other way. You gave me more. I want less light. Okay, that's good. So this is a particularly sophisticated cell phone camera. They're not all like this, but in addition to the zoom lenses and things that you might get, there's a very, very sophisticated not CCD, but CMOS cameras that are buried within these things. So these are cameras that are made on the same fabs that make integrated circuits, and they figured out ways to do that. I'll come back to that a little bit later. So that's more photonics inside the cell phone. But we're not even at the big pieces of photonics. The big ones are the integrated circuits that go in there. So some of the most advanced integrated circuits in the world are now inside your cell phone. The size of the market for cell phones is so huge, and the money going into that's what's driving mobility, low power, high density is what's driving advances in electronics now. So all the things you've got in your pockets and mobile gizmos and stuff are putting now 5 or more billion transistors on a single chip. And the only way you could ever do that is with the print engines that are done with lithography. And now they've got EUV lithography printers that can go down to nanometer scale dimensions. So the current commercial node in silicon is about 14 nanometers, 140 angstroms. That's the feature size that you find inside these integrated circuits. The wavelengths of these EUV systems are around 13 nanometers. So they've got a long ways to go before they run out of steam with these latest nearly X-ray kind of sources. And they're frankly a pain to use, and they haven't become widespread because the lithography needs to be done in a vacuum. And that's no fun, trying to put big wafers into vacuum systems just to do the printing. But we have students and faculty members who work on the technology that goes into these. One of the companies that works on this is ASML. They're the leader in this, and they have an operation both in Europe, but also in Connecticut, and then their unit that makes the laser light sources, actually, they're not laser light sources, they're plasma light sources fired up by lasers, is in San Diego. It's called Cymer Technologies. And they often frequent the college here to try to steal our best students to work on this kind of stuff. Again, we haven't hit the big one yet, so this is really the big one. So when you go and make a connection and try to do a scan or a search, you're connecting up with wireless to something nearby, a nearby base station, but very quickly you're going into the fiber backbone in the US or even around the world. And that fiber optics, the core of our internet communication technology is photonics. It's fibers, it's semiconductor optoelectronics, it's lasers, detectors, modulators, and so forth. And I'm going to be talking a lot more about that as the talk goes on, because I do want to take a couple of really deep dives in some areas. Just to give you a sense of where this field is right now, in the leading research systems in the world, people have demonstrated that they can take a single hair-thin fiber and they can cram 1 petabit per second on a single fiber, 10 to the 15th bits per second. If you do the math, that's enough for every U.S. household in the country to be downloading on their Comcast connection at full bore on 1 fiber. And for those of us who've been in the communication field, to even kind of get our head around that, it's impossible. It's gone up so many orders of magnitude since the 1980s when I first went into this field. So it's really just an astounding amount of progress. And if you look what the internet is, we're always hung up on these fibers going between continents, going across the countries and so forth. But the reality is that the internet looks like that. It's these huge data centers that look like football field size warehouses that are just full of computers, row after row after row of computers. And guess what? They're all wired together with fiber optics. Each one of these servers has fiber connections that go into switches that route the signals all over the place. And there's nearly 1 million lasers inside one of those data centers. So the internet is all about photonics. It's all about fiber optics. It's all about semiconductor lasers. It's detectors. And this is all about the internet. So, you know, when you think about photonics, you should think about something that's as important to you as this. You probably don't go anywhere without this. Yeah, optics is your eyeglasses too, but this is where there's a lot of action in our field today. So, so when we think about photonics, you'll get a different answer from anybody you talk to. What's the difference between photonics and optics? Generally, we like to think of photonics as being applications where the particle nature of light is important. You need to understand that it's a photon rather than just a wave of energy. Just because you use photons doesn't mean that you don't lose the wave properties, and that's the subject of quantum field theory, which some of you may have already been exposed to. Others may have that ahead of you, to really understand the dual nature of both particles of matter and particles of light. And it's all one cohesive theory where you finally say, okay, I get it. I understand why they all behave the same way and why it's all described by the same mathematics. But if we think about photons and so forth, most of the applications where that turns out to be important are where you're converting light into some electronic excitation. And when you do that, you realize that you can't build up low-energy photons to create a high-energy photon to excite an electron. The photon has to be big enough to do it, and that's the quantum nature of the electronic states in the medium that you're dealing with, but it's also a feature of the light field itself, that it's made out of photons. So things where that's true are lasers, LEDs, photodetectors, you know, the photoelectric effect. I'm sure many of you or most of you have heard of that. The whole field of optical communications and fiber optics, guided wave optics, and things we call photonic integrated circuits. And I'm going to go into that in a lot more detail in a minute. Fields like nonlinear optics, some of the physicsy applications of emerging things called plasmonics, and that's where you use metals, and you're really treating light more like the way we think of antennas and radio waves, but scaling it down to nanoscale dimensions. And maybe Ewan will say a few things about that in the next talk. And then optical and optoelectronic materials are a very, very big part of photonics as well. And I could probably keep that list going for another couple pages. So this is what we kind of generally think about when we think of the world of photonics. And to be a guru in the field of photonics, you need a tool belt. And when you come to graduate school, you know, your first year will be spent boning up and building up this tool belt, and you'll be learning about in more depth. So you've probably had these courses already, but you might be taking more advanced versions of them, of quantum mechanics, electromagnetic theory, optics. To design some of these solutions, you need to know often a little bit about electrical engineering. You might need to know a fair amount about semiconductor device physics. And then just to be kind of complete, you might want to throw in a dash or two of some of these other fields of quantum field theory. It's interesting because there's not very many fields where all the advanced physics you learn, you actually use it to design and engineer solutions. So we learn about quantum field theory because we want to understand, you know, the real meaning of life and what's the real physics behind these things. But you don't think you're going to use it to design something like a cell phone. And the answer is, yeah, you actually need to. You can't understand this stuff without understanding some of these theoretical foundations of modern physics in a very fundamental way. And I'll give you maybe a couple examples of that later on. So some examples. The rest of this I'm going to talk about applications just to give you flavors of what some of these things are. One of the things we're kind of proud of here at the College of Optical Sciences is that we are the lead institution in something called CIAN, which is probably can't read that, it's the Center for Integrated Access Networks. It's one of these things the National Science Foundation calls an ERC, an Engineering Research Center. So they're kind of 10-year vehicles where you get lots of millions of dollars per year to put together a large team of collaborators across the country and pursue noble goals. In our case, we lead the only one in the entire United States on optical communications. And it's together with UC San Diego, Caltech, UCLA. Who am I leaving out? Well, we've had Cornell on there now. Columbia is a strong member as well. So in this center, we pursue kind of all the facets of the field of optical communication. Some of that has to do with architectures. So when you lay out and you want to communicate to different nodes around the country or different nodes within a data center, different computer servers and so forth, you have to have a strategy about how you're going to optimize the network to make sure it doesn't get clogged up with not enough capacity. How do you do it efficiently? How do you do it without hogging power? If I go back to that, often these things are located right next to hydroelectric dams because they need cooling water and they need power. A few percent of the entire U.S. Electrical consumption is now used in the data centers, used in the internet. And there's a statistic, I think if you do a mouse click about 20 times on the internet, like on Google, it's enough, you've just boiled a cup of coffee somewhere. That's how much power you're using to do that. So trying to come up with solutions where we are being more efficient and more cost effective with energy. In fact, even all those computers I showed you, half the cost of a data center today is in the total power consumed over the life of the data center. It's not all the fancy boxes and computers. It's the power. So that's a big problem. So trying to come up with architectures that solve that is a big deal. Here at the university, I don't know if any of you saw this lab, but we have a test bed which actually emulates long-distance communications racks with many, hundreds of kilometers of fiber, and then you can hook up switching systems and racks with all the lasers and information systems, and access that at a certain point with your new widget. So if you've got some cool new device that's going to slice bread better than anybody else, or it's going to be faster, better, lower power, you can try it out with probes in a real network environment and find out whether it really works or not, without having to have it be completely commercialized and set up with a beautiful commercial package. So this is part of the need in an effort like this, is to have test beds. We have advanced device work all the way down to plasmonic nanolasers. So this is some great work that was going on at UCSD to make these little nanoscale pillars of metal with semiconductor wrapped around and then buried in a oxide and metal clad. So it's like a tin can coaxial cable, but nanoscale, and it makes lasers that are so small that you don't even really see a threshold in them. And all kinds of clever devices that can route traffic. So you come in with a whole bunch of traffic, and you need to divide it up into 10 different directions and be able to switch and control that at will. And so there's all kinds of clever ideas about new and better ways to do things like that. So that's what Cyan is all about. When we think about optical communication technology, one of the really big advances in the last 25 years was the advent of what we call wavelength division multiplexing. So it used to be, actually I said this to a few folks at lunch. When I was first went into the field, I was about 10 or 12, and I got a Time magazine at home. I don't even know if, I guess it still exists. It's kind of a rag these days, though. But it used to be a good magazine. And on the cover, there was this picture of laser beams and optical communications. And as a 12, 13-year-old kid, I said, wow, that's really cool. You mean you can, I knew about radio waves. I know a little bit about FM modulation and all this kind of stuff. And I said, you mean you can really do that with light at a frequency that's, a million times higher? You can really do that? That's amazing. I got to learn about that. And I was so crushed when I got older and found out, no, it's not like that at all. They've got these optical fibers, and there's people sitting on one end going like this, bink, 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 oh, bink, and it's Morse code. That's all it was at the time. I mean, it wasn't literally Morse code. It was digital ones and zeros, and it wasn't like a carrier with FM modulation or any of that stuff. It was really crude. And nevertheless, it was still much faster than what people could do with radio waves. But me and hundreds of other people like me went about the mission for the next 20, 30 years to make that a true statement, so that it really was like radio waves, and we really could do all those things. One of the steps along the way was wavelength division multiplexing. Used to be you had one guy sitting there going like this, and it went in a fiber and came out the other end, and that was your one channel. Well, people figured out that if they wanted to have more than one color at a time, they could do that. The light doesn't interfere with itself, mostly. I'll show you that it does, unfortunately. But if you have two colors in there, they both go in the fiber. They don't even really know about each other. So you can have a whole bunch of transmitters, each one at a different wavelength, and combine them with like a grating, for example, or some other device to get them focused into one fiber and send all that information. But the problem is you can't go very far. And so what people needed to do, if they were going to do that, would be to divide it back out again, detect each weak channel. It was about to get to the point where you couldn't even tell what a 1 and a 0 was anymore. And you would clean it up, and then you'd retransmit it. But if you had to break them all out again and then do a digital regeneration of each signal independently and then combine them again, it was just ludicrous. Well, along comes this amazing device called the erbium amplifier. And this is a fiber-based device where you put in an active medium and you pump it up just like you would a laser medium, but you don't put it in a resonator. So it's a gain medium in a laser without a resonator, so it doesn't laze unless you're sloppy and you get an accidental reflection, then darn it, it will laze. But you make it so it doesn't laze. You put in isolators and things like that, and you can amplify, boost all of those signals at the same time without having to separate them out again. Well, that made a huge difference in the economics of high-capacity communication systems. So this was a revolution in the field, and we pursue that kind of stuff here. To make fibers, you need to be able to put together what's called preforms, and you combine all these materials together into a glass rod that has all the cross-sectional structure of the final fiber you want to make, and then you put it in this thing called the draw tower. And it's kind of like when you pour maple syrup on your pancakes, and a little thread forms, and you pull the jar away, and the thread gets really skinny as you pull it away. Well, that's what happens with this hot glass, and you can pull it out, and if you do it really uniform rate, it maintains that entire structure as you pull it down, even though it gets reduced in dimension by many orders of magnitude. And that's how you make fibers. And what we do here, and others doing research in this area, is try to work with new materials so we can get gain in a fiber amplifier or make a laser out of a fiber amplifier at new wavelengths, not just 1.5 microns, or 1.3 microns, which are the sweet spots for optical communications, but at wavelengths of 2 or 3 microns, or maybe shorter wavelengths around 1 micron, and so forth. So fiber technology turns out to be really important, in large part because you so efficiently contain the light in overlap with the gain medium. You can get a very long propagation length with very low loss. And when the light comes out, it's a single diffraction limited spot. It's a single mode in this guided wave. So if you want to make a transmitter for outer space communications from a satellite, you probably are going to end up using something like a fiber laser because it controls the light so beautifully. So we work in areas like that. There's also microstructured fibers where people are making fibers with cores that look like Captain Crunch cereal or something like that. And they have unusual propagation properties that people take advantage of. I mentioned light. So photonics is also nonlinear optics. And I'll give you some examples in the context of optical communications. This shows two colors that are launched down a fiber that are only 1 angstrom apart. That's about 12 gigahertz, 12.5 gigahertz at 1.5 microns. And they look, you can separate them out. After 120 kilometers, they still look pretty good, but then you look at 600 kilometers, and all of a sudden it's starting to look a little trashy. And if you go further to 1,000 kilometers, it looks like garbage. And you go 1,500 kilometers, and it's almost unrecognizable. This is because fiber is not a linear medium. So when I said you put two colors in and they don't know each other there, I lied to you. So what's really going on here? Well, these two wavelengths go into the fiber, and they're so close together, there's an intensity beat between them. So there's a rhythmic beating of the intensity in the fiber as those two things co-propagate down the fiber. And when the intensity gets bigger, this medium is called a Kerr nonlinearity. It changes its index of refraction with intensity. So that means the fiber index of refraction is going modulating at this beat frequency. And either one of those signals, when it goes down in a medium that's dynamically doing that, it creates sidebands. And that's what these things are. So these form their own grating in the fiber, modulated grating, and then these things scatter off it, and then they scatter, and these scatter off those, and it just gets worse and worse and worse. So that's bad. And it limits how close together you can have the channels. More importantly, it limits how much power you can put in a fiber. And ultimately, that limits the capacity. If you want to have lots and lots of information, that means each bit of information is a really short time. That means it doesn't have very many photons, and you have to decide if it's a 1 or a 0. Well, if there's only a couple of photons, how do you decide? You can take a guess that was probably a 1, but you might not be right. So power, if we could put more power, we would increase capacity, and this puts a limit on that. So when you study the world of optical communications, fiber optics, photonics, you'll end up probably learning a lot about nonlinear optics. It's not all bad. Here's an example where you can do something good with exactly the same phenomena. So if I put a high-power pump laser in there, and then I stick a signal in there, or I stick an idler in there, these two beat together, and they will create a signal over here. If you put these two, they'll beat together and create a signal there. It turns out if I put this pump in there and I seed a signal here, that small nonlinearity will actually draw energy from the pump into the signal. It's an amplifier. So you can make an amplifier using this effect. It's called a parametric amplifier. And they work quite nicely. So this is another way to do amplification without using something like erbium, multi-level atomic systems. This is amplification based purely on a dielectric medium with no absorption, no anything. It's just due to this nonlinear response of the glass. And this shows theoretical calculations and some experimental data from a colleague who's over at Chalmers University working in this area, a guy named Peter Andrickson. So people now use this in some instances in real communication systems to boost up signals at wavelengths where erbium doesn't work so well. Also, you can project the amplifier out into the fiber. When I have an erbium amplifier, it's right here. I pump it and it sits right here. With this stuff, I shoot my pump, and my pump goes 20 kilometers down the fiber, and the amplifier is actually in the fiber. And that means as the light's getting attenuated, it's getting boosted up. That has some advantages in noise in an optical communication system. So what else do we do in fibers? This shows some work from one of our faculty, Con Q, who's devised a way to make mode-locked lasers. These are lasers that put out very short pulses of light. You'll hear more about them tomorrow from Jason. And normally, these are big tabletop systems that cost hundreds of thousands of dollars, and they're really expensive, and they're power hogs, and you can't make small portable systems out of it. And he found a way to make mode-locked lasers in something that fits in the palm of your hand. And it's done with, the clever part is inside here, there's a little bit of fiber that's been reduced in diameter and coated with carbon nanotubes, of all things. Why carbon nanotubes? Well, it turns out they make a really great saturable absorber. And this is something that when the light comes in, it gets absorbed. But if the light's really intense, it stops absorbing. And it turns out that phenomena will induce short pulse formation inside a laser cavity. So using a device like that, he can generate short pulses. He can generate super continuums of light, and this is useful for things like there's fields called optical coherence tomography that you'll hear about tomorrow, I think, from Jennifer Barton for biomedical diagnostics, but just in general for short pulse applications. So here's an example of a pulse that's only 14 femtoseconds. That's only a handful of optical cycles, and this is something that he makes these in his garage. and it's a little business. And if you want to buy one, I think they're about 10K, something like that. Maybe he'll give you a discount. But it's way better than these big things, and they're really stable too. So people love using them in experiments because they don't have to be tweaked and adjusted. They just work. And so he's used them in other things like microscopy. So when you have really short pulses of light, again, you can use nonlinear optics. It turns out when you look at something like third harmonic generation, it's very, very dependent on the intensity. So if I have light that's being focused down, the intensity will only be strong enough right at the focal point to generate a third harmonic of light. And what you can do is take the focal point and move it up and down inside a medium and look at the third harmonic dependence of the medium and actually image that. And these are movies, but I didn't make the movie part on my laptop. These are 3D movies. So this is the 3D movie of the end of a mosquito's a little pointer needle, and this is a fly head, and they're all three-dimensional rotating movies. Very nice. They're now even looking at brain tissue and being able to resolve nerves and so forth in three-dimensional form using this technique. So it's opening up new capabilities in microscopy. Again, normally that would take tables of expensive electronics. It would not be something a typical medical operation could use in a diagnostic environment, but when it's this little handheld thing, you could think of doing that. We have work on detectors here. This is a fellow named Mike Lesser who makes some of the largest focal plane arrays anywhere on the planet. This is a 100 megapixel example right here. And these are made in silicon foundries, but then they come here in wafer form and they get diced up and put into modules, sealed up into hermetic packages, and they get deployed all over the world. He's got these, this shows where they are deployed at telescopes and scientific instrumentation all around the globe. So really knows what he's doing in that field, and it's an important capability for the university. We also have other novel cameras. We were talking at lunch with some of your colleagues about polarization imaging, and this is some work from Stanley Pau's group where he takes a CCD image or a CMOS camera and makes, on each pixel, makes little micropolarizers that not only can resolve states of linear polarization, but states of circular polarization. So that's pretty unique. And what that means is you can image something on a pixel by pixel basis. You can resolve the complete picture of the polarization of light in the image that you're looking at. And that has all kinds of interesting applications. Russell Chipman told me at lunch today that Sony just invested in a capability very, very similar to this. Probably thinking about the future of things like autonomous vehicles, where knowing whether or not there's ice on the road and things like that is going to be important. Places where polarization makes a big deal. So let me now dive. The rest of this talk is going to be a pretty deep dive into something very close to my heart, and it's the world of integrated optics and what we call photonic integrated circuits. So integrated optics has a very long history, starting out with materials and people making waveguides in glasses and dielectrics and ferroelectric materials like lithium niobate. For a good decade or two, getting fairly primitive devices, but eventually getting things to work quite nicely. So there was a lot of tools that came up. There's mathematical techniques called coupled mode theory. There's all the analysis of waveguides and how do you find out about leaky modes, and how do you analyze the not just optical fibers, but in planar waveguides and things that you use in devices. So these analysis tools became very important. People developed all kinds of clever new components and ideas for making filters and waveguides, and eventually a lot of active component development. And that's what I'm going to talk a little bit more about now. So there were two, kind of going back into the 1970s, 80s, and early 90s, there were two kind of undisputed breakthroughs that really had a major impact in the field of guided wave optics. And one of them is a guided wave modulator. So this is a device shown here in lithium niobate where you put light in. And if you see these dotted lines, these are the two branches of light. So it splits and it goes down two paths, and then it recombines again. And by putting a voltage on lithium niobate, it's a electro-optic material, you can change the index of refraction with voltage. So if you change the index of refraction, that'll change the phase of the light that arrives here. And when it gets to that Y intersection, either it recombines in phase and they go merrily on their way here, or if you delay the phase of one of these, they'll arrive out of phase, and it turns out that kicks the light out of the waveguide and it just goes flying off to the side. So that is how you make a zero. You can extinguish the light that way. And to make these really fast, you design them so that the electrical transmission line shown here, it's called a strip line. It's like a coplanar strip line, and you can arrange it so the velocity of the electrical signal is pretty close to the velocity of light. And that way, when the signal is going along here, if there's a high voltage point right here, it travels with the light and it doesn't get out of sync with it. So it turns out that makes these devices much faster, and people demonstrated things up into the range of 50 gigabits per second, and so using modulators like this. The other major advance was in semiconductor lasers, and I'm going to talk a lot about that in a minute, but this shows what's called a distributed feedback laser, and it's a semiconductor laser that has a waveguide that puts out light at one frequency. And it goes back to what I said earlier. We don't want light to just be a burst of light. We'd like it to be a carrier that we can encode phase information and intensity information just like you do with radio waves. And a laser like this can actually put out a tone that's pure enough so it really behaves like a sine wave just going down the fiber. So how do you make things like that? Well, again, photonics is also about materials. So here's an example of a molecular beam epitaxy machine. I just yanked it off the internet over the weekend. It's not the one we have here. We've got one upstairs. It was just a nice picture. But the way MBE works is you have elemental materials that you heat up in a fusion cells, and they just evaporate atoms. And the atoms come flying out in high vacuum, and they land on the substrate. And when they land on a heated substrate, they'll actually relax, and they'll form into, if you come with the right composition of materials, it'll form into a nice crystal lattice that matches the underlying substrate. This is called epitaxy. When you grow material on a crystal, and the new material you grow lines up with the atoms on the crystal below, it maintains the crystal structure, and that's called epitaxy. If you just deposit a film and grow it like an oxide or a piece of glass, that's thin film deposition, but it's not epitaxy. So this is a very important epitaxy technique. It turns out the real breadwinner of the field today is something called metal organic vapor phase epitaxy, and this is a system where you flow hydrogen and materials like arsine and phosphine over a substrate, and as they go through bubblers, they pick up elements in suspension, and when they land on the surface, they will lay down with the atoms, again, lined up with the underlying material. And that's not just a story. This is an example of a transmission electron micrograph showing a quantum well made between gallium arsenide phosphide and indium gallium arsenide. And if you look here, you can see this is where the material changes, and all these columns of atoms line up perfectly. So this is really a remarkable phenomenon that you can do this and change the composition of the material as you grow. There's more to it than that. There's a lot of advances that took place in the structures that people use to make good semiconductor lasers. One of the most important was this idea of what's called a double heterostructure, and I didn't think to make a diagram of it, but if I go back to this quantum well, this material here might have a lower energy, or what's called a lower band gap, than the surrounding material. So if I look at the energy diagram of this, it would go along, and then it would have a well in it. And if I put electrons in there, they get stuck in that well. So the electrons are there. Well, what these guys discovered, and it gave them a Nobel Prize. So it's a good field to be in if you want to go to Nobel Prize. So this is Alfarov and Kromer. Herb is out at UCSB. Zoris is at the Yaffe Institute in Russia. they discovered that not only would you contain the excitation in this well, but because that had a higher index of refraction, it made a waveguide. So you've got a high index material surrounded by lower index material, and that means when light moves down there, it'll totally internally reflect and it'll be guided. So the light is guided in exactly the same place as where the excitation is. Makes a beautiful laser. So this became something that dramatically changed the efficacy of semiconductor lasers as a reasonable light source. And then there were later advances to make quantum wells and then quantum dots and so forth. So many, many orders of magnitude improvement in the efficiencies of these materials. And all of it's enabled because there were a lot of wizards that figured out how to make better materials. I was one of the device guys who thought I was really clever because I could design a cool device. The reality was it was enabled by people who spent decades of really hard work coming up with really good materials. When they got it done, they said, here, try this. And it pretty much no matter what you did with it, it was amazing. So you didn't have to be a genius to come up with good devices when you had amazing material development behind the scenes. And also structures. So here's an example of some colleagues from Bell Labs, a guy named Herwig Kogelnick and Chuck Shank. And they came up with this idea of what's called a distributed feedback laser. So normally a laser has a gain medium and two mirrors, right? And so the light goes through, gets boosted up, hits the mirror, comes back, and it would grow ad infinitum, except the gain material saturates. So at some point, the gain equals the loss, and it just can't get any bigger, and that's when it's steady state lasing. But it turns out you don't need mirrors. You can make feedback continuously along a waveguide if you put a grating along the waveguide. So light goes along and it reflects off each tooth of the grating, goes backwards, and a little more goes backwards, it goes this way, and then it gets reflected back and it comes back. So you get continuous feedback along the path of a waveguide if you put a corrugation or any kind of a periodic disturbance in the index of refraction along the waveguide. So this was an idea, and they had the notion that they could make mirrorless devices and semiconductors and integrated optics, and boy, they were right. So here's an example, again, of this modern day distributed feedback laser. This is the waveguide along this way. Here's the grating. There's quantum wells in it. It's all these tricks that I was talking about. I'll go into a little more detail. So if we look at end on, this is what this thing actually looks like. This is a diagram to show you what you're seeing there, but this is a scanning electron micrograph of the actual laser structure. And you can see there's a whole bunch of layers there. The middle one right here, so this is end-on view of a waveguide. It's a little strip that goes along the length, and if you stick light in there, it'll propagate down this waveguide along the length of the laser. And because of the grating there, it'll get feedback. But if you look carefully, not only is there this active medium, but there's all these other blocking layers, and these are tricks that people came up with to prevent current flow. So you need to do this, you need to know about semiconductor device physics. This is p-n junctions, current flow, and if this is a p-n junction, this is all p material in here. So this is a forward bias p-n junction. It excites that gain medium, works like a charm. If you try to go this way, you've got a p-n structure. That turns out that's like a thyristor, and it doesn't carry current. So you can have a low resistance contact across the whole surface, and all the current has to move along here and then go shooting through this hole. So people came up with really clever designs like that. If we look sideways at this, and now I've turned this thing sideways, here's the waveguide. Down underneath here is this corrugated material. So people came up with techniques to grow this, to etch teeth in this grating and then grow more material on top of it. So this is a buried corrugation, and that's what gives you all the little reflections as you go down the length of the device. If I take a dive a little bit deeper and I look at this thing, you see here's the material there, and then here's all these quantum wells in there. So this is what's called a multi-quantum well semiconductor laser. So all that stuff that I was showing you earlier gets built into this technology, which is now inside this, inside everything. So in fact, almost all lasers now are pumped by semiconductor lasers. If they're not electrical to start with, they're optically pumped by semiconductor lasers because they're so darn efficient and reliable too. This idea of engineering quantum mechanics kind of got taken to a new level also in this field. In the example I'm showing here, it's called a quantum cascade laser. Again, another colleague at Bell Labs, Federico Capasso, and his group championed this. But the idea is a particle in a box. How many of you have taken quantum mechanics? Okay, a lot. So I would say more than half, 2/3. So if you've got a particle in a box, you've got a ground state. First excited state is a wave with a node in the middle, and so forth. But they have different energy levels. So if I do this business with heterostructures, and I have a narrow bandgap material here and surrounded by higher bandgap material, I've got a particle in a box. And I can control the energy separation between the first excited state and that ground state just by the thickness of the box. So I can engineer that. And if I put a whole bunch of these in a row, I can send current in here, it'll get de-excited, and if I line it up just right, under voltage, this thing will inject efficiently into the next one, and I get to reuse that electron over and over again for each well as it goes along. What's kind of neat about this is the atomic transitions of this laser are completely man-made. This is not it's not an atom or something where somebody said, oh, that has the right wavelength. This is completely engineered structure. The wavelength separation associated with that photon is given by the width of the quantum well that you engineered. So in reality, they're more sophisticated than that. You can see the active regions here, but there's a lot of layers in there to equilibrate the excitation and get it to efficiently flow to the next one, injector layers and all kinds of stuff. But this is now real, and all of a sudden, when we didn't used to have 5-micron lasers, now you can go out and buy a 5-micron laser, room temperature, and it works, and they're all over the place. So innovations in this field move really fast, and they get commercialized really quickly. Integrated optics. So 45 years ago, 1969, there was a nice paper in, you can see I'm Bell Labs centric, in the Bell Labs Technical Journal where somebody kind of prophesied that we could do this integration in optoelectronics. And the vision was that we could put a whole bunch of components on a single substrate. Just like we do integrated circuits with electronics, maybe we can do this with lasers and waveguides and so forth. Sounds cool. It turned out it was quite hard to do. But the vision was there, and it slowly started to get realized. Here's a really simple example of a laser and a modulator. So here's that DFB laser again, and then here's a modulator. And this was an example of just two components being brought together. So how do you figure out how to do this? Well, the one I showed you there is based on something called the Franz-Keldysh effect. So if I look at the band structure in a semiconductor, this shows an absorption event where I elevate an electron from the valence band into the conduction band. And the idea of the Franz-Keldysh effect, again, I have to use my tool belt. I need semiconductor band theory, quantum mechanics, and so forth. But it's basically a tunneling phenomenon. If I have a photon that's not energetic enough to make the transition, then the material is transparent. Light flies right through it. If I put a voltage on that, that means the energy states are really sloped in space. That's what happens when you have an electric field. The energy gets higher when you go in the opposite direction of the field. Well, this transition says, oh, I can't make it. I'm transparent. But then it says, darn it, if I was only 50 angstroms further away, I could make it. Well, that's the nature of quantum mechanics. You can't localize things that carefully. So this thing tunnels over to this state, even though it doesn't have enough energy. And the more voltage I put on that, the more likely I am to be able to tunnel that. So that means when I crank up the voltage on this, the absorption is going to go up. I was in an office when so you're going to go into graduate school next year, probably. My first year in grad school at Caltech, there was a second-year grad student who said, I'm reading this thing called the Franz-Keldysh effect. I think I might want to try to make a modulator out of that. And I said, that's really stupid. That's like science fiction. Come on, give me a break. And so he moved on and did something else. Turned out to be, at the heart of the internet. It turns out. So kooky ideas, you should pay attention to them, and they do make a difference. So how do you calculate this thing? Well, it turns out, again, you turn the crank, you do all your band theory, all these calculations, and using straightforward stuff that's easy to learn, and you'll learn it. You come up with these closed-formed expressions with airy functions in them and all this stuff, and you can plot out what the absorption looks like as a function of voltage based on just doing the math. And it turns out it really works, and not only can you get the amplitude, but you can get the phase. And it turns out amplitude and phase are coupled. It's a causality relationship called the Kronig relationship. And so the phase matters because when you extinguish the light, if you also change its phase, that means you're sweeping frequency. Phase change with time is the same as frequency change. And when you change the frequency, then that means the light spreads out and it causes a mess in the fiber. So again, that's the simplest case of integrated optics, combining two components together, a laser and a modulator. It was done, big hit all over the internet, worked wonderfully. And there it is again, that's the device. So I didn't talk about how you did that. Here's the quantum wells, and the way you go from a material that has gain into one that's transparent is you need narrower quantum wells. Again, the particle in a box. If the quantum wells are skinny, the states are farther apart, and so it can't get absorbed because the states are too far apart. So how would you actually make something like that? Well, it turns out people are very clever, and they came up with a crystal growth technique where they found out that if they covered part of this is a plan view, top down, if they covered part of the substrate with oxide, the vapor phase constituents in the growth don't like to land on the oxide. They want to land on the material they're ready to grow on. And so what that means is they hover around here, and when they see the opening, they go, that's where I want to land and grow. So it grows thick here, and if I look along there, that would mean in this region it would grow thick. In this region, the same material would be spread across the whole surface. So this would grow thinner quantum wells. Well, there you have it. Here's a picture along the length of a device. Same growth, same thing, and skinny quantum wells, thick quantum wells. So you can make modulators that way. All kinds of devices then started getting made. Tunable lasers on a single chip where you can change the index and phase of the cavities and gratings and so forth and sweep frequencies around. Even, this is some of my own work, even this is 1989, made the very first coherent heterodyne receiver ever. I still have that chip sitting in my dresser at home. I hope it might be worth something someday. Because now these are all over the internet as well. So these things did get commercialized. As I showed in high volume, tunable lasers are all the rage now. When it's a wavelength multiplex system, nobody wants to have a laser that's just one channel. They want to have a laser that they can tune to whatever channel they want. So all these ideas for tunable lasers became very important. Photonic integration also finally took off. So this is some work from a company called Infinera, founded by some colleagues of all of ours here. And they were able to take all these individual components and put them onto single chips now. So these are kind of like electronic integrated circuits. Here's a view of one of the sections of a chip that has, it's got, I think, 20 different lasers on there in that little millimeter square section. So hundreds of optical elements on a single chip. And as I said, what people are now doing, they're not just turning light on and off. So this is a picture of the amplitude and phase of an optical field in the complex plane. And with on-off keying, like this, I'm just going between an on state and an off state, going from 1 to 0, 1 to 0. But if I can treat the light like a carrier and control phase, I can encode information in not just amplitude, but in phase. And I can do it in two polarizations at the same time. Or I could even have 16 different states in one polarization and do this with two polarizations. So you can start doing all the same kind of encoding that people do on radio waves now with light waves. And this is really happening. And here's an example of some of the latest chips from that same company, 500 gigabits per second. And this just shows one channel of the receive side where there's a DFB local oscillator that beats with the incoming signal and goes into sets of detectors to detect the amplitude and phase of the encoded signal. And this shows the output diagram of all the different channels. And now they're putting these things in, most recently, just this year, they now demonstrated something that has much higher capacity, 16 QAM, that's the constellation diagram I showed you a minute ago, 2.4 terabits per second transmitted from a single little chip. So it's pretty amazing technology. And now people are trying to do it in silicon. So that's all compound semiconductors. And why would I try to do it in silicon? Well, it's because in the world of silicon, people have refined manufacturing and fabrication technology to a level unlike anything else in the history of mankind. Quite simply, there's just $40 billion a year goes into R&D in silicon microelectronics. You're not going to repeat that investment very often in the world. And so the question is, well, it's a crummy optical material. It doesn't laze. It's not electro-optic. But maybe I can still do something with it. And the answer is, yeah, you can. You can do a lot of cool stuff with it. So people started making photonic integrated circuits in silicon. This shows because the index between the silicon and the air is so large, you can make things really small, and you can bend light on a micron scale without having it radiate and have losses. So you can make really, really small things, little resonators. You can make detectors with germanium. Turns out germanium was already in the silicon fabs because people used germanium in high-performance transistors. And people came up with ideas to make modulators based on plasma effect in a silicon. When you have free carriers in a material, they can move when you put an electric field on them. That means they're polarizable. As soon as you have a polarizable plasma, that means it has a susceptibility. That means it has an index of refraction. So by changing the carrier density in a semiconductor, you do change the index of refraction. It's not a conventional electro-optic effect, but it turned out it worked great. So people started making modulators, and these got commercialized in the last decade. And it's going on as we speak. So earlier this year, these are some friends of mine from Bell Labs, and they just IPO'd their company called Acacia, and their market cap was already up to about $5 billion based on silicon photonics inside their coherent communication modules. Some other friends, this was my office mate at Bell Labs, and interestingly, my son's roommate from UCSB, and they co-founded a company called Orion that was just acquired by Juniper, and it was a way to bring compound semiconductors into silicon fabrication and be able to make things using indium phosphide and so forth on a silicon platform. Intel just announced that they're finally going into high-volume commercial production on their silicon photonics. So this stuff is real. We were excited to participate in something that tried to capitalize on this, and it was part of President Obama's manufacturing center initiatives called the National Network for Manufacturing Innovation. And a bunch of us thought this was a really ripe area for investment for manufacturing, so we made the case and were awarded what's now the largest one of these institutes to date. So we're part of the leadership of that, and our leadership team got to meet Jumpin' Joe and shake his hand, and it was a lot of fun. But what we're trying to do with this thing, so a lot of major companies are collaborators with us on this, the Intels, IBMs of the world, and so forth, the company Infinera I mentioned, and there's a leadership team of the universities here that are kind of leading the charge on this. The headquarters is in Rochester. That's really because the facility in Albany, New York, this is a university clean room. Doesn't look like a typical university clean room. It's a multi-billion-dollar investment previously by IBM, but the state of New York, to have a state-of-the-art silicon fab. It's this entire complex, and now we're dedicating a lot of those resources towards doing photonics and photonic integrated circuits. And where we're going with this is to be able to offer all these fancy components. This is a big laundry list of all the things that we would be able to make. And the idea was over time we're going to offer what are called multi-project wafer runs, where you can sit at your desk with a design kit and design some application that uses modulators and lasers and detectors and waveguides all over the place, and sit there with a design kit and say, yeah, that's going to work. You'll submit it to the fab. It'll come back, and the chips will come back all diced up to you, just like integrated circuits today. So that's where we're going with this project. One of the major areas we're still tackling is in assembly and in packaging of these things. The company Infinera I showed you, when they hook up, so the photonics is all integrated now. It's wonderful. But they still have to hook it up to the electronics. So how do they do it? They have a whole bunch of wire bonds. And this is incredible. It's just layer upon layer. These can't touch each other. So they're all stacked up along the whole length of these things in order to get the connectivity between the electronics and all the photonic components that are on that chip. So part of what we want to do is to realize this vision here of stacked three-dimensional photonics, where we have digital electronics that might be the drivers and sensors and so forth, and then the optical components would be on a different layer. So this is kind of a dream that people had, and the question is it real? I invited this fellow who's no longer CTO at Intel to give a keynote talk at a conference I chaired, and one of his messages was that the only thing that really makes something happen for real is when it's a high-volume consumer application. Then companies invest the manufacturing technology to really have it be stable and take it to the bank. You can always do custom solutions, but they're going to be expensive, and they're not usually as reliable and so forth. So you want to make things reliable like this. Well, it turns out, so what drives technology? I don't know how many of you have seen this movie. It's pretty old by now, well before you were born. But it wasn't when I was born. I was quite taken with it, and of course we always wondered what this thing was that drove innovation. Well, thanks to the advances in modern science, we've been able to figure out what it was. And yeah, it was the cell phone. That's what it was the whole time. So there we are with our cell phone again. And why am I saying that? It's because the technology that's inside the image sensors, the CMOS cameras, high volume application, is using what we call through silicon vias. So we have the CMOS image sensing chip here. We have the image signal processing chip underneath here, and they're connected three-dimensionally with these micron-scale pillars that go through and connect up the different circuits. So this is two integrated circuits stacked on top of each other, but it's actually done at wafer scale. So there's machines now that can actually do this and take a whole wafer. These are now, they're 12-inch wafers. And you can turn them upside down and bond those two interfaces together to be able to realize things that look like this. And so we want to be able to do that in the world of photonics. And my message that I've been giving to the community is you've got to forget everything you knew about these little gold module boxes that we put components in, and we've got to ride what commercial electronics gives us. And now commercial electronics is giving us this three-dimensional capability, and if we can bring that into the world of photonics, we'll be in very good shape. Fortunately, the team we put together for this manufacturing initiative, the reason we cherry-picked the team we did was because some of the folks working on it, in particular between Albany, SUNY Polytechnic, and MIT, they were already doing this. So they had a DARPA program where they had 12-inch wafers where they were putting CMOS directly on top of photonics and combining it into composite three-dimensional chips. So they promise really, really low energy for things like the internet. You don't have parasitics of voltages trying to go over here to some optical component. It's right there with almost no capacitance connected to the next device. And the density is incredible. So not just for communication devices, these are now being looked at for making arrays where you could have 1 million pixels and have each one be amplitude and phase controlled with the controller circuit underneath it. What's that? Well, it's a hologram. It's a display. It's a LiDAR engine generator. It's whatever you want it to be. So you'll see this technology not just in communications, but all kinds of stuff. So photonics is awesome. That's the end of my message. We try to make that message clear on our website. So if you go to our Lighting the Future video, you go in there about, I think it's about 3 minutes.
Every year at graduation, I tell our students they're the Jedi Knights.
So people think I was kidding about that. What we didn't realize is that when we were filming the video, one of our students was actually using one of our lightsabers. And there he is. There he is. So go into the video and check it out. We didn't want people to know that we do this kind of stuff here, but that's what photonics is too. It's just awesome stuff. Sorry for the bad jokes. That's it. Thanks. And I ran a little bit over, but I'm happy to take some questions if you have any.
some of your slides, it said 50 ohms, and then it had,
Yeah.
why?
That was a message I was trying to give. It goes back to usually you have transmission lines in electronics, and when you send electrical signal down a transmission line, you have to terminate it. So if you have a 50 ohm, very common in high-speed RF signals to have 50 ohm transmission lines, but every time you have to terminate it, that's a heater. An example would be if this microprocessor in here had a 50 ohm termination on every transistor, it would melt down this building. It would take about a 50 megawatt generator to run it. So how can you get rid of terminations? Well, you get reflections and things like that. But if you make things so intimate, the electronics is right there with the photonics. It doesn't matter if there's a reflection. It's a lumped element. And so the idea of electrical intimacy means you can get rid of all that terminations and kind of a transmission line mentality. Good observation. All right, I'm a little behind, so we should probably move on. You're going to hear more talks.